Okay, guys, let's start. So, GM Warsaw, my name is Justyna Broniszewska, and I would like to welcome you to the second meetup. And let's start. Thank you. Let's start from, I will remind you, just quickly, our rules that apply here. So first of all, be kind and respect others. And the second of all, we won't tolerate shilling or sales pitches, so be aware. And our goals as the ETHWarsaw Foundation are, as you can see, is educate about Web3, help others discover new Web3 talents, and we would like to put Warsaw on the map of great Web3 events, and by that contribute to the global Ethereum community. And how we want to do that? Here you can see our roadmap. We started with our first meetup. Today is the second meetup, and the first part of this roadmap will finish in September on a conference and hackathon. So I would like to invite you all to this hackathon and conference and see you there, hopefully. This is all possible by our team, and big applause for them. They're somewhere there. If you want to talk to them, ask them about what we are doing, just reach them. And here is our sponsor. So we are actually part of the Ethereum Foundation's road to DevCon. So yeah, thanks to Ethereum Foundation, we are all here today. Without further ado, let me present you agenda for today. We'll start with Piotr Szlachciak's presentation about scaling Ethereum with rollups, and then we'll go to presentation of Jakub Wojciechowski, and he will tell us why are oracles crucial for DeFi. And after presentations, I would like to invite you to grab pizza, drinks, and to just networking. So please enjoy the second meetup. You can reach us on Twitter, our web page. So please welcome Piotr and Peter. The stage is yours.
I'll use this mic,
Okay.
but I need to set up my gear. Okay, fantastic. Welcome, everyone. So today we're going to talk about scaling Ethereum with rollups. And I've structured my presentation a bit like an investigation. We're going to figure out why, we're going to figure out how, and then we're going to figure out some more spicy stuff about what's actually going on. But first, we're going to start at the end, at the big diagnosis. Blockchains are ill, unfortunately. They've fallen ill because we are all using them. We're all using them, and they can't handle it. The blockchain cannot scale on its own, right? Even if we try to, increase its parameters, make it process more transactions, make it do more things, bigger gas limit, lower block times, it actually won't solve the problem. It will just decrease decentralization, and the increase in performance that we are going to get is really not enough to handle what we actually need to scale. So what's the solution? Rollups, okay? End of presentation. No. Blockchain is like a train. And you probably haven't heard this metaphor before because I invented it while I was making the presentation. The main idea is that the train cars are like blockchain blocks. So each time a new block is added, right, a new train car is added. And the locomotive is the node. And the reason this metaphor works is because the locomotive, the node, has to handle all of the weight of all of the blocks. It has to actually carry it. It has to process all of the data. It has to store all of the state. It has to do all of the work. And the more we put onto its back, the more blocks, the heavier it gets and the harder it gets. And this is why it actually increasing the load on the nodes reduces decentralization, because you just need to have a better locomotive, which is to say a better node. And in fact, the metaphor goes even further, because the train cars as blocks actually allow us to visually represent what's really going on when we stack transactions into blocks. Because you can imagine transactions actually as, some packets of goods that are being transported. And the train car, the block, actually only has, a limited space. And we, as discussed, cannot increase that space because the decentralization will suffer. So we need to figure out how to stuff it the best we can to figure out, to fit the most we can. And we need a mechanism to actually decide how much cargo can we put in. So here we have an abstract way to visualize that. Each rectangle here is a single transaction, and the block can fit, I don't know, it's, I think, 8 transactions here. Some of them are larger, some of them are smaller. We still haven't talked about how do we measure it. And it turns out the way we measure transactions is actually crucial for enabling rollups to work. Because I don't know if you know, but in Bitcoin, the transactions are just measured by size. The bigger your transaction is in terms of bytes, this is a bit of a simplification, but let's say the bigger your transaction is in terms of bytes, the more it's going to cost, the more it's going to weigh, the more it's going to take up block space. But in Ethereum, your transaction can be actually very small. It can be just, I want to trade this token for this token on Uniswap. But then when you actually execute it, it does all of the things. It transfers the token, it calculates the different pool values, it transfers the token back. All of this calculation is going on. So we need a different measure. And here is another metaphor that I came up with while doing the presentation. Actually, the way we measure the transaction cost in Ethereum is a bit like going to a beauty salon, right? You go there and you want to do, I don't know, your hair or something, and then you go through the list and it's like, oh, okay, I want to do long hair, but I'm a man, but I also want to do the beard, but not nails, and you sum it all up, right? And you get a total. And in Ethereum, it's actually a bit of the same. So I've summed up some of the more common operations. So if you want to do just a simple transaction, just a value transfer, you're gonna pay 21,000 gas. By the way, gas. It might sound weird. I think the name is very bad. To me, it should be named as computation units, and then nobody would be confused what it is. It's just computation units. It's just a unit of measure. So the transaction costs 21,000 gas. Each byte of call data, which is the call data is basically what the transaction is composed of. So if you want to call, for example, the Uniswap contract to swap tokens, you're going to give the contract some instructions to say, hey, swap this token for this token. And these instructions are what is call data. So for each byte of call data, it's actually only 16 gas that you pay. For reading values from storage, which is each contract on Ethereum has its own database structure, where it can save some values. So for example, each token has its own little database where it stores how many tokens each user has. Now, to read how many tokens a user has, you have to pay around, it depends, but around 2,000 gas. To actually write to actually give some tokens to a new user, you have to write the value to storage, which costs about 20,000. And then if you want to create a new contract, it costs 32,000. So all in all, to sum up, all of those values, if you do some operations on the mainnet, you probably want to change some state. You want to change some storage. Maybe you want to deploy a smart contract. You definitely want to send a transaction. All of this adds up. And as you can see, to do anything, it costs a lot of money. The verdict, how to deal with this, is to do as little as possible on chain. But, if we don't do things on chain, where do we even do it? Does it even happen anywhere? If the chain doesn't know how can it even work? And so the first part to understanding rollups is the pricing. And keep in mind that the call data is very, very cheap. This is going to come in handy later. The second part to understanding rollups is the state transition. So, you know, blockchains are hard. There are many moving parts. But if you think about it, what happens on the blockchain is actually really, really simple. It's this formula. The next state of the blockchain, of every contract, of every account, of everything that happens, is just whatever was there before plus whatever transactions users made. So a simple example would be, you know, before I had 1 ETH and my friend had no ETH. And then, so this was the previous state. Now the transaction would be I transfer half ETH to my friend. And then the next state is, of course, I have half an ETH and my friend has half an ETH. So the same thing applies to basically anything that you do on the blockchain. And here comes the ingenious part about rollups. If you know the initial state, which most probably is nobody has anything, and then you add up all of the transactions that happened, right? So someone deposited money, someone transferred money, someone swapped money. Then you just actually need all of the transaction data to figure out what's the final state. You don't actually need the state, you just need the data. And so while you execute on the main Ethereum chain, you pay for both the data and the execution. You can actually not pay for the execution, you can just have the data. And then you can calculate the state yourself in the background somewhere else. And then you have a very, very cheap way to do transactions. So here is where the metaphor of the trains and cars of trains goes too far. Here is a block with rollup transactions. And each rollup transaction is just the data, no execution. And then the execution is kind of like tagged along like this balloon attached to this transaction. Because what the balloon represents here is that we can do all of the computation of chain, right? We know the previous state, we know the transaction data, and we can compute everything off chain. So the balloons don't actually weigh the train down and make it possible to have even more done with the chain. And we have just one issue with this entire approach, right? So far we've discussed the following. We have transactions, but we only use the data to describe everything that's happening. We then use those transactions to construct the state. So if we want to, for example, deposit money, we'll just say, okay, a transaction on L1, layer 1, I mean the base Ethereum blockchain. So here, a small definition of terms, L1, layer 1, the main Ethereum blockchain, L2, layer 2, the rollup, the chain that's, you know, constructed from all of this data. If you want to deposit money there, it's easy because all we do is we have some data on L1 that says we deposited money, and then we can actually, you know, apply it just as any transaction data to calculate the state where I now have more money. But what if I want to take the money out? So far, we've assumed that we can calculate on the, all of the state ourselves. So, you know, we can do it off-chain. We can not worry about anything. But there comes a point where we actually would like some money back, right? And all of this optimization, if it doesn't allow us to do anything with the state, it's kind of pointless, you know? It's like, oh, I have some data, I calculate some state, I need to get it back. And here, another nice thing from the blockchain space is going to help us out is the tree. And of course, in IT, trees grow upside down. And this is actually a Merkle tree. And a Merkle tree is a very simple data structure. It just uses hashes. It's like hashes all the way up. And at the very bottom of the tree is the state. So this is where you can see that, okay, I have some ETH, or, you know, I have some tokens, or the Uniswap smart contract has some pool balance, something like this. Then you take this state, you hash it, and you take a state of another account, right? You have two hashes, you hash them together, and now you have a hash representing a state of two accounts. You take the hash of the next two accounts, you hash it together, you have the state for 4 accounts. You hash it however many times you need, and then you have one root hash, right? One single small value that represents the entire state of the entire system. Okay, so we have this value. It looks random, but how do we actually, now get the stuff out of this tree? Well, here is where the hashes are very important, because with hashes, you can construct Merkle proofs. And, all of these terms are super fancy. Merkle proofs are just the hashes along the way. So if you want to prove that the user balance is in the tree, you just need all of the hashes that are used alongside. So if I have some balance, I need to know the balance of the neighbor in the tree so that I can compute the hash on the next level. And then I need to know the neighbor hash on that level to compute the next hash. And then if I know all of the hashes and the original value, then someone else can recalculate all of the hashes up to this point and compare the hash that they got with the hash that the hash of the entire state. And this is what Merkle proof is. If the hashes are correct, then it means that the value had to be in the tree. So let's say I wanted to cheat. I wanted to say that, I actually have more ether than I have in this tree. Well, I wouldn't be able to do it, because if I posted the proof that I have more ETH, then the actual hash value at the end of that proof, when someone recomputes it, would be different from the correct state hash. So then, to withdraw money from this rollup construction, all we need is to put the resulting state root of the entire rollup chain on the main blockchain. And then we can just say, okay, I have some money there. I can prove it to everyone because I have the Merkle proof, and I want that money out. This means that we have now established a way to have a cheap chain, right? Because we only pay for the data. It's running completely in parallel. It doesn't disturb the main chain. And we can go in because we can have a deposit transaction that, is counted like any other transaction, just data. And we can go out because we have the state root, and we can do a Merkle proof that we have the money. And that's the end of our worries, right? No. So it turns out that someone has to compute the state root, someone has to put the state root on chain, and we need to have a mechanism to figure out if it's correct. Normally, when you have a blockchain, you don't worry about such things because every node in the system actually runs all of the transaction, actually computes all of the state. So everybody knows the state. And if someone would try to, state an incorrect state, then nobody would accept it. But with a rollup, we have a different situation. We have a situation where someone says the new state is this, right? The new state is like, a hash of 1, 2, 3, 4, 5, 6, 7. Okay. And then we need a way to figure out if he's lying or not. And there are two approaches. And we're going to start to talk with optimistic rollups, and then we're going to move to ZK rollups. The optimistic approach is actually really simple when you think about it. It's, we're going to assume the hash is correct. Someone has posted the hash, it's going to be fine. But we're going to give a window of around, let's say, 7 days, where we assume that there is at least one person in the entire world that actually has computed the state, has checked that it is the same state hash that someone has posted on chain. And if the hashes are different, that this one person will post a transaction on chain claiming, I challenge you. I want to go to court. I want the blockchain to decide. And this is the idea of fraud proofs. So with optimistic rollups, as I said, we assume that the state root is correct. But if it isn't, anyone can challenge it. And to make sure that everyone is sufficiently incentivized, we require anyone who wants to propose a new state root to put up a bond if you want to have your state be the new state, you need to actually put some ETH as collateral. And then if someone would say, oh, you actually, did something wrong, maybe you cheated, maybe you have an error, maybe I don't like you, then they can challenge, right? And they also have to put up a bond. And then it's time for the final showdown. The blockchain has to decide. And, here comes the tricky part, because the blockchain cannot just execute all of the transactions, because that would defeat the entire purpose of the scaling solution. If anytime we find something is slightly incorrect, we have to re-execute everything, then we just pay the same cost. So we need a smarter solution. And the current state of the art is we actually do sort of an interactive game between the block producer, who claims that this is a new state, and the validator, who claims that actually the state was incorrect. And they together figure out through, I don't know the name of the algorithm, where you split into twos and then you figure out something in the middle. It's like binary search. Exactly. Through binary search, they figure out the exact moment in the calculation where something has gone wrong. And then the blockchain has to only execute this single step in the entire execution. And this is how you save money on validating everything. Instead of validating all of the execution, you first require the block producer and the validator to figure out where they actually disagree, a single execution step. And then you execute just that step, and the blockchain just decides, because it now knows either the block producer is correct or the validator is correct. And then one of them loses the money. Oops. And actually, it happened. And it happened to us. So, Chris, who's somewhere among you, I don't know where. This is Chris, who's also the co-founder of L2Beat, has done a hack. The idea was to steal real money. And the real money in question was nothing short of $8. Now, why was it $8, and why did we even think that stealing them was possible? Well, there is this optimistic rollup called Fuel. And Fuel is amazing. It has nice technology. It allows you to, as I just described, transfer money between people, deposit, withdraw. It's optimistic. It has all of the execution of chain, all of this good stuff. It has just one problem. Nobody uses it. Literally no one. So the $8 that was there was sitting there for over a year. No activity, nada, right? And we thought to ourselves, well, it's going to be a good PR stunt, right? We're going to steal the money, and we're going to say to everyone, you know what? Optimistic rollups are great. But what about optimistic rollups where nobody watches the chain? And we thought to ourselves, we are so smart. So we created the master plan. The master plan was to become a block producer. We posted a bond, 0.5 ETH, to steal $8. We posted the bond. Now we posted a fraudulent state transition, a state transition that assigns the $8 to us. The final part was about to begin, a 2-week wait, where in the constant anticipation of the impending reward, we would sit and wait for the time where we could send the deposit transaction. But actually, the instant that we sent the fraudulent state transition, it turns out that the chain was not abandoned, and the validators for the Fuel optimistic rollup were actually there all along. And so instead of getting $8 in the sweet, sweet, hacky payback money, we lost 0.25 ETH. And, I had to put off buying new clothes. I had to eat less this month. But the story is nice, I think. So anyway, it turns out that actually, even though a chain can have zero activity on the main Ethereum chain, it can look completely dead because of the way optimistic rollups are constructed, the construction is still secure if there is at least one person anywhere, somewhere, willing and able to check the state. And the QR code is if you want to read a more technical description of what happened. And so this was the first thing, right? Optimistic rollups. We put the state. We assume it's correct. Then we fraud proof. Now comes the ZK rollups, and this is an unfunny joke. Two rollups walk into a bar. The barman asks, "Can I see your IDs?" Optimistic rollup says, "If nobody can prove I'm underage in 7 days, that means I'm over 18. And ZK rollup says, "I can prove to you I'm over 18, but I won't show you my ID." And this is the main idea behind optimistic rollups. Behind ZK rollups is that the main way we actually save on computation is that instead of doing all of the computation, we just have a proof of correctness. And the proof of correctness is zero knowledge because it doesn't contain all of the information about what was actually executed. So the real fun part of zero knowledge is that it actually alleviates a problem with optimistic rollups, because when we have the optimistic rollup, it has this small issue that because there is a window in which everybody and anybody can challenge the state, that means that we cannot assume actually that the state has been fully checked, fully correct, until the window closes. And only after the window for checking the state closes, we can allow someone to withdraw money from this construction. So usually, if you just want to withdraw money from an optimistic rollup, you have to wait 7 days. It sucks. For zero knowledge rollups, because every time you post a new state update, you actually have to create a zero knowledge proof that every execution that you did was correct. That means that as long as the blockchain can check the proof, you don't have to wait to withdraw. The state is immediately considered valid. So it's absolutely great, and it's also super complex. Here is an accurate depiction of what happens when you create a ZK proof. It requires a lot of math and a lot of things that I can't explain. And this is why I think it's magic. And this all sounds great, right? You have optimistic rollups that are simpler to build, but you require some waiting. You have zero knowledge rollups, more complex to build, but you have some nice properties. And now you're thinking to yourself, why am I paying the L1 Ethereum fees? What am I doing wrong with my life? I just want to use the rollups. Where can I find the rollups? And, not all is great, it turns out. And this is a screenshot, and the screenshot is made to look like part of the page, but it's a screenshot from L2Beat, where it actually shows the risks of using the different solutions, because there are many solutions out there that we could potentially call rollups, but they're not finished. The technology I described to you is not done. It's not fully researched. It's not completed, as in, you can just deploy it as any smart contract and you have a rollup. There are many challenges that have yet to be overcome. And some of them are because the fraud proofs and the ZK proofs are actually quite complex to build. I did some hand waving for the fraud proofs that you can, bisect all of the execution to find the single execution step and then execute it. It turns out it's not that easy, right? And then for, zero knowledge, the proofs are actually also quite complex. The mathematics behind it is complex, but also trying to mimic what the blockchain does in the first place with all of the intricacies of the EVM, like reverts or, message calls between contracts, or, having different account types for externally owned account and contracts. There are all different considerations that you have to take into account when building those proof systems. So it's not that easy. And so here come the challenges. First challenge is that if you are an operator that, if you're a developer that, has built your own rollup, and as you all know now, that it's not finished. You have to, constantly develop it. You have to potentially fix bugs, add new features, all of the good stuff. So you add a way for yourself to change the code. And I mean, it's justified in a way. As I said, you have to fix bugs and you have to add new features because it's not finished. But on the other hand, as Dua Lipa says, I've got new rules, right? If you are using the rollup, the operator can just come out of nowhere and say that all of the rules that you assumed were the rules of the game up to this point are now changed. The upgradability mechanism doesn't really differentiate between an update that finally does the fraud proofs correctly and an update that says all of the money that users deposited is now mine. To the smart contract, all of them just look like updates. And so there's inherent risk, even if we assume that the developers are completely benevolent, if their keys are stolen, if they are manipulated, for example, through external coercion, governments, kidnappings, stuff like this, then you have an issue of what happens to the money in the rollup and what happens to the smart contract and the rules inside it. Moving past this, if your systems for proving are kind of like unfinished, maybe a bit proprietary, you don't want to open it up to anyone to use or abuse, right? Because if you have a system that's kind of ready, maybe ready, you don't really know, you have a lot of tests, but you would like more, then what do? Well, you say, okay, we're gonna do it live, but with a check. Only a group of trusted friends is gonna be able to use that system because, as a developer, you have some confidence that they're not gonna steal the money. So if you are an external participant and you figure out something's wrong, right, and you want to submit a fraud proof, for example, where you're like one of those ladies trying to get into this club. No, you need permission and you don't have one. So this is also, in a way justified, because if there wasn't those permissions, then someone could abuse vulnerabilities in the system and potentially also steal money. But it's another thing to consider. And the last part, as I said, is the proofs are actually complex. And the reason the proofs are complex is mostly due to the EVM. Because if all you wanted to do is transfer some tokens around, it's not that complex. You just need to, subtract the value there and add the value elsewhere. But if you want to do arbitrary Turing-complete execution of smart contracts, well, it's another story indeed. And if you really want the L1 to be able to re-execute some parts of the execution, L2, you really have to implement the EVM in the EVM, which is not fun, let me tell you. And so, but this guy likes it. And with zero knowledge proofs, it's kind of the same. Although you're not implementing the EVM in EVM, you're implementing EVM with cutting edge maths. And I don't know, it's not fun also. Maybe some people like it. I think it can be fun, but it definitely isn't easy. And, so we have the nice technology, the nice vision, but we also have the issues, right, with the ecosystem. And now, for the finale, it's up to you, right, to do something about it, to contribute to this space. And I think, there are many ways to contribute. One of the ways is just to learn about it more. There are many resources that I'm going to talk about in a second. The other way is to, once you've learned something, you can become a researcher in this space to either figure out the different solutions that are there or try to push some of the research either in the zero knowledge space or in the fraud proof space, or there are even more areas, for example, resource pricing that I completely haven't mentioned. you can also, if you know some DevOps skills, right, use that, because there is a lot of infrastructure that needs to be run. And, this might be useful. And then if you just want to develop smart contracts, then you now have an entire new domain that you can use for your applications that has a bit of a different trade-off, maybe at this point less security, but also a lot cheaper transaction fees, which means that the opportunity for what you can do with the smart contracts is bigger. And then if you're like, really into building low-level stuff and you like languages like Go or Rust, you can build the L2 infrastructure itself. And now for the resources is actually where you want to learn this stuff. And, I have this blouse, and together with Chris and many other people here, we've created L2 Beat. And this is a resource that's, mainly focused on education and research. And so we recently did a conference in Amsterdam. We have a website, we have a Twitter, and we are also looking for, people eager to be more in this space. And with that, I thank you very much for being here. And I don't know, Justina, if we have some time for questions or anything, but yes? Okay, so we can have some questions if anybody has some. Oh, we have a question there. I don't know if we should run around with a mic or
anyone can use the microphones on the tables. So just feel free, press the button and speak.
Hello, what will be the price of Optimism token? Thank you.
So it will be between 0 and infinity. Thank you. Although with recent developments, saying it will be between 0, I don't know, it's hard to say. There are different things happening in the blockchain space. Sometimes tokens are worth 0 actually. So maybe between 0 inclusive and infinity.
Any other questions?
Yeah, hey. How does progress a computation fee in ZK rollups?
How does gas work in ZK rollups?
Yeah.
So
I mean computations. Is it linear progression or maybe some another?
No, so it's actually very different, and it depends on the rollup that you use. Some rollups try to actually mimic the EVM, so they'll try to be as close to what Ethereum actually does as possible. So when you develop on them, you would be just writing a regular Solidity smart contract, and the resource pricing would be basically similar, because it would be just a different table for the different opcodes in EVM. And some are actually completely different, like, for example, Starknet, where you have their own different language, their own different pricing, and it really varies depending on the rollup. So there is not one easy answer. You need to press the button.
What are the L2 solutions you're most excited about?
That's a good question. I think that I'm most excited about the upcoming ones. So there, I think, are 4 that I'm really watching to see what they're gonna do, which is, one of them is Starknet from Starkware, one of them is ZK Sync 2.0. The other one is actually Arbitrum and Optimism, because they are about to run some big upgrades, and I'm really keen to see how they turn out. But it doesn't mean that they are the only ones. I think, for example, there's going to be Fuel V2, there are going to be some other chains, like Arbitrum AnyTrust chains, and there's even some Reddit chain in the works. And, Loopring, as always, has some updates to their exchange rollup. There are many, many different solutions. And I think at this point, and it's, a meme in blockchain, but we're early in the, layer 2 space. And I think, that means that there are no clear winners yet. Go ahead.
Yeah, one more question. Is it any actually reason that optimistic rollups should exist. I mean, the only cons of ZK rollups in comparison with optimistic ones is only the complexity, as you've been saying, right? But I believe we can sort out it in a few years. So any real reason?
So the real reason is the timeline, and the timeline is such that the ZK rollups are not fully ready yet, and of course.
So when they get ready, optimistic rollups gonna die.
Well, that's one way. It's not as obvious because the optimistic rollups can get really optimized, and the 7-day withdrawal window is actually only if you want to do it through the main bridge, but there are many ways to circumvent that, and so I think that it's not as clear cut. Of course, as you said, ZK rollups have clear advantages, but the advantages are not as pronounced, and if optimistic rollups get optimized enough, they, I think, will still be able to compete. Of course, in the very long term, we would probably expect that ZK rollups are the, let's say, winners or will have process majority of transactions, but I think it's not settled yet, and I don't think it will be for a long time.
Can I add something? Does it work? Okay, so I think this is much more nuanced that, ZK rollups are gonna be like the real shit once they are ready, right? It's not like this. Like, people are underestimating the fact that optimistic rollups can be extremely efficient when things go well. Like, you don't do anything. With ZK rollups, you always need to verify the proof, right? You need to do it always, even though things are perfectly fine, right? And there's this thing that ZK rollups can scale better because they just can prove the state diffs that were broadcasted on the chain instead of like all transactions. And this is the one of the scalability benefits. But this also means that they lose accountability of the blockchains of L1s because you don't post all transaction data on chain, you just post state diffs. And this is different than what optimistic rollups are trying to do. So it's much more nuanced than, ZK tech is better.
Other questions?
Yeah, let's do one last question.
Yeah.
So, as we all know, the only way to really scale blockchain is through rollups, as you have explained in your presentation. But do you see any other projects on working on the rollups on other blockchains, L1 blockchains, and
Yes.
then on Ethereum?
Definitely. I'm gonna strongly recommend you also learn about the Lightning Network, because I think it's a completely different and really interesting approach to scaling a blockchain. It, at this moment, I know there are some works doesn't really do smart contracts, but it's great for payments, and I think that it's really worthwhile to read up about it.
What do you think will happen with other L1 blockchains when rollups will roll out on Ethereum?
Well, it depends, but the future is hard to predict. But most other L1 blockchains are not really innovative because they're like, okay, let's do Ethereum, but let's switch one thing to have a different trade-off. And if you really want something to be successful, you're gonna do like 10x that. Not really in terms of this 10x transactions. It's just 10x better in every aspect: developer tooling, the speed, the possibilities. So if you just have a blockchain that does more transactions, it's not innovation, in my opinion. So this is why I don't really see a reason even right now for other L1s. Okay, thank you so much, and give it up for Justyna.
Yeah. Thank you, Piotr. And now please welcome Kuba. Big applause for him.
Hi guys, thanks for coming. Thanks for having me. Congrats to amazing talk. Not only super interesting, but also I'm intimidated by the number of funny memes and puns that he used. This is going to be more boring, but I try my best. So let me tell you something about oracles. What's the purpose of oracles? What are the common development patterns? And how do we try to innovate the space? So let's start with the oracle problem. Let us imagine a DeFi without oracles. So a metaphor would be like buying a new laptop without an access to internet. So solutions like stable coins, something like DAI, without the knowledge of what's your true collateral won't be possible. Solution like Aave, when you are taking a loan against your collateral, also won't work. Also stuff like option settlements won't be possible because you do not know what's the strike price. It's very similar to leverage in investing and trading. It's really hard to close your position if you do not know what's the actual value of your assets and what's the value of your margin. So the whole blockchain will be pretty useless, at least in the area of DeFi. So I hope I convinced you that in the DeFi space we need oracles, but why do we need a dedicated service? Why cannot every smart contract simply directly call an external API and query for a price of Ethereum or Bitcoin? So let's imagine we got a few thousand of nodes and every of the node is calling an external API and trying to get a price. It will be a total chaos. So far, some of the API will give an answer at a given time, some will give a bit earlier, some a bit later. Also, some of the queries will time out and it will be extremely hard, almost impossible to achieve a consensus around the answers. Also, calling an external API from a blockchain node, which is supposed to be fully deterministic and secure, it's asking for troubles. So we need something better. We need a dedicated service that will provide us price in a secure way. And how it all started. So when people realized that we need a solution to inject external data to blockchain, it started with a very simple pattern, with a two-phase approach when you get a request and a response. So first, the contract is requesting a piece of data, then a dedicated service is listening for that request, prepares an answer, and put it on chain. It works quite fine. There are still solutions like that in production, but there's one really big problem. So the experience of using a protocol that is implemented that way, it's not very pleasant. It's like going on a train with Piotr, and when you order a meal on one station, you need to wait on another station to get part of the meal. Then you order another meal, you wait to get to another station, and then you can have, let's say, a supper or a drink. So the journey wouldn't be so nice, and definitely it breaks the user experience, but also it affects the composability because you got delays and asynchronous calls in the smart contract execution. So there was another attempt. So let's assume that we got all of the prices in place, on chain, delivered, and fully persisted. Yeah, life is super easy. You simply query for the price, you get it from a blockchain state, and that's it. Fully synchronous execution, super convenient for developers. There's only one tiny problem. Who actually delivers all of the price data and who pays for the gas? It's like super heavy. It's like, yeah, it's really hard to put all of the information in that train. The train won't be able to run, and the bill for putting all of that data will be super huge. But it happened. For the most popular tokens, as you probably know, the current market leaders are syndicating the cost, but still the bill is extremely heavy. On a time when the gas price is really high, the bill can easily extend $1 or $2 million daily. So we tried to mix both solutions and have a convenience of the synchronous calls, but without paying for the storage. So that's our approach, and what's the magic? How can we avoid putting all of the data to the storage and actually simulate a situation when the data is already there? So we use a very hacky way of passing the price information. So as you may remember from the pure presentation, there's one structure in the menu that you've seen that is actually very cheap. It's called call data. So our approach is to put all of the pricing information in the call data. So when you start to execute a transaction, there is no price data. But executing a transaction, you can foresee what kind of information will be needed. And then off-chain, we append your transaction in a hacky way, adding some extra information to the message data, to the call data, with the price information, and forward delegate further the user transaction. Then on-chain, we verify the data that it comes from a trusted source, checking the signature, and actually make it available for consumption for any blockchain protocol. So from the point of view of a developer, it looks as the data was on-chain. For the point of view of user, it also is very convenient because there's almost like no delay and the transaction can be processed synchronously. And that's the screenshot on how actually we are calling the external services, getting the signed data, and we append the message. And also as a side effect of this pattern, as I mentioned, we do not touch the storage of a target chain. Therefore, the exactly same architecture could be applied to various blockchain. And as you know, we got at the moment dozen of layer 2 solutions. And also we got quite a lot L1 solutions and blockchains that are longing for the price information, but it's impossible to put all of the data on all of the chains. That's why having this lightweight approach, in our view, could be more scalable in the current blockchain landscape. So as you can see on the picture, we get nodes that take the data from external APIs, then we deliver them to the target chains. Obviously, there might be a question, what's in the middle? How can we securely pass the information? So it's kind of a relayer problem, and we wanted to focus on that to protect it against different kind of attacks. So it cannot be DDoS, it cannot be spammed, etc. So we use like different layers of transmission. Some of them are based on simple caching. We also leverage decentralized protocols for data transmission, like Streamer, very interesting PubSub protocol. And what's the point of doing that? As I mentioned, putting data directly on chain is extremely expensive. So we compare the cost to the most popular solutions available. And if you look at the storage cost, there is a huge difference. It's not an order of magnitude. Actually, the price is 1,000,000 times cheaper because we leverage for the storage not only our relayer network for the short-term storage, but also Arweave, which is a chain dedicated for storing data for the permanent storage. So we have a full accountability of the price feeds, very similar to what's happening on chain, but at a fraction of a cost. So the difference is around 1 million, and actually, yeah, I think that the chart is corrupted, but that's how close I can get to 1 millionth with a single pixel. And let me show you some code. So let's imagine that you are building a marketplace for NFTs. Probably a quite common use case in blockchains recently. Thousands of people are spinning off their own protocols for trading NFTs, and that's very simplistic one. You simply post an order, you cancel an order, you get orders, and you get a price for an NFT. Or you can simply buy an NFT using for convenience a native currency like on OpenSea that you pay in Ether, which got a lot of advantages. For example, transactions are really cheap and it's easy to implement. And let us take this solution and try to make it, to upgrade it in a way that you can buy an NFT whose price is denominated in USDs. So it will be better for sellers to post that NFT and not to realize that in a week time they are getting like 1/3 of the price they intended to get. So in order to do that, you need to implement a price-aware interface, which actually use some fancy logic in assembly code that I'm not going to describe, but all of our code is open source, so please take a look. That verifies the signatures and extract the price data. And also you are responsible for the validation of data provider. So the simplest way to do it is just to trust one of the provider, but obviously the logic can be much more complex. You can trust one among many providers, or you can randomly pick a provider or use any logic that you intend for your protocol. And when you do these two magic steps, then you can simply query a price as convenient as the price was already on chain. Also, there is one additional step on the client side. So whenever you are interacting with a contract that implements that interface, you need to append the transaction with the price data, because in our case, the users are the one responsible for passing the message. So they are paying for the data transmission, which is a very low cost, and they are smuggling this Oracle data. So for that, we extended the ethers.js library, and you simply wrap your own contract and specify what kind of price provider you are going to use. So what kind of data can you already access? So at the moment, we got more than 1,000 assets. We integrated with more than 60 sources, and we persisted permanently more than 3 billion data points, so everyone can check the history, the accuracy, the reliability of the service. So that's one of the examples. The price of Ethereum when we merge across more than 30 sources and deliver the median price on chain. Also, what is really interesting, recently we provided a way to specify your own custom Oracle and do it using a web interface. So we prepared that for the Hack Money hackathon that happened recently. There were like few projects using that solution. There are various use cases, like let me maybe try show you. So some of them were about okay, custom URLs. Some of them were about the weather data, if you are going to build an interesting protocol utilizing that. But what I also found funny, one of the protocol was implementing a life insurance, and then got an endpoint that was saying whether a person is alive or dead. That was a pretty scary, but actually a very interesting use case. So maybe that's the future of the blockchain. And to give you an example of, let's try to create a lightweight Oracle. Maybe let me use an OpenSea API. Okay, what's interesting? Let's get some collection stats. Let's work. Yeah, there's something there. I'm pasting the URL. Try to evaluate. Yeah, you get some answer, and then you specify a JSON path to get the data. Okay. And what can we get? Maybe a floor plan. Okay. So we got a full price. Then you get specify the name. Oh, what kind of collection could it be? I get that. Okay, Doodles official. Is anyone in NFTs? Is it a good collection? I don't know. But let me subscribe to that. And then we deployed a service that every minute will query the API, sign the data, and make it available to use in your contract. So if you are building a derivative on the price of NFTs, that's the way to go. also what's interesting. So apart from these funny use cases, there's one protocol that already is using the solution to protect real money, real funds. And it's a prime brokerage trading protocol on the Avalanche network, which also is compatible with our solution because it's EVM compatible blockchain. So simply you can borrow some money with a collateral up to 5 times the amount of your collateral, and you can use it for trading, for staking, etc. So you can leverage your yield farming if you want to. And they're using our oracles to constantly value the total assets owned by user. So even the stake tokens could be valued in the real time. And if the value of the assets to the value of the collateral drops below a safe level, then a liquidation bot can close a position and protect the solvency of the whole protocol. So actually the usage is really simple. They just derive from our contract and they call a get price from message method. And yeah, so far so good. Touching the wood, obviously, but that the protocol is live since 2 months and we haven't experienced any hacks. I hope that Chris is not hearing that. So also, how do we store the configuration of the data providers? And it's a lot of data because we need to specify what kind of assets a data provider should deliver, what's the probing interval, what kind of data sources, etc. So there's a lot of data and we'd like to have this solution fully decentralized. So all of that is managed through smart contracts, but putting that directly on a network like Ethereum would be very expensive. That's why, as I mentioned, we use Arweave network, which is amazing for storage in regard of the actual storage cost per data item. And we build an extension on top of that that allows to execute any arbitrary logic. So it's kind of a rollup solution built on top of the storage network. In our view, makes like a total sense because for the base chain, you definitely and basically need very efficient storage and the execution can happen off chain. So that's also like a super interesting product that we are working on. I'm not going to tell you the full story. It's a fascinating research, like how actually can you execute arbitrary code when only the inputs and the code of the contract is persisted on chain. So the code is executed off chain in a lazy way and then delivered on demand. So I'm just putting this as a preview. Maybe if we are lucky to be invited for the next time, we'd love to tell you more about it. But it's based on the WASM execution layer, and we built a lot of tools like a transaction browser, way to put randomness for the contracts, etc. And actually, despite it's like super early, apart from us using that for oracles, there are a few other projects that are using that already in production, prominent projects on the Arweave network. So I think that's all. So thanks for the attention. There are the links if you're interested in the Oracle problem and how we tackle that. If you'd like to learn more or work with us, we are more than happy to tell you more about the project and the company. So thanks.
We have time for a few questions if you want. Any questions? Yeah.
Hey, what's the main killer feature of Redstone that differs from a Chainlink, for instance?
Definitely. So as I mentioned, there are these operating costs. Like with Chainlink, you need to put all of the data on the target chain, and the most popular chain at the moment is obviously Ethereum. So as I mentioned, the bill for a daily gas cost could go up to $1 million or $2 million, and definitely at such a high price, you can only support the subset of the tokens. So the blue chip tokens like F, BTC, so up to probably 100 tokens. And the less popular one are refreshed with much larger periods. And with our solution, if you're interested in the price of any arbitrary coin, the long tail, or simply, to put it simply, the shit coins, if you want to build a solution based on that, you can do it because it's much more affordable. As I said, the difference in cost is probably 1 to a million.
Hi, I want to understand a little bit more. So, as I understand, there is no way to get Oracle data if we are, for example, doing transaction between contracts, or we are not doing the transaction from the external owner account or like front end, where you off-chain wrap the data in the transaction. Is that correct?
Yeah, that's correct. So you need to also amend the entry point. It doesn't need to be a front end, it could be a script, it could be any solution. So at the point when you are submitting a transaction, you need to also integrate with us. So that's the cost. As a benefit, you got this scalability. That's yeah, well spotted cost.
Thank you.
I'm interested to know, you said that the data comes from a trusted source, I believe. And I would like to ask what the trusted source is. Can anyone become a provider for Redstone Finance, or do you only run your own nodes that call the APIs?
Sure. So everyone is invited to become a provider, but the duty of a provider is to publish a manifesto. So what sources are you using? What's your methodology? What's your interval period, etc. And that's persisted. That's a public knowledge in our contracts. And then you are being kept accountable. So if you deliver an incorrect price, you can be punished for that. So in order to become a provider, you need to stake some tokens as a collateral. And there is a dispute mechanism very similar to how the rollups are resolved. So you prove that the data was wrong, and then the dishonest provider could be punished.
Just to follow up, I'm interested in how you prove it. Is it a voting-based system?
Yeah, so at the moment it's token-based voting system, but we are exploring the common solutions in the space. So there are like two paths. One is to use the trust execution environment, which is quite heavy to implement. Another one is to have a notary proofs of the TLS communication. So that's another approach. And we are working to automate that, but at the moment the dispute resolution is a manual dispute process that could be escalated with a rather crypto-economic mechanism involved than a purely technical verification of a proof. So it's more on the optimistic layer compared to the rollups rather than the zero-knowledge proof.
Okay, thank you very much. If there are no more questions, I would like to thank the speakers. And before I let you go to the wonderful food and beverages that we have, I would like to thank the Warsaw University of Technologies Faculty of Electronics and Information Technology, my own also, for letting us use this space, which is wonderful. And also I would like to thank the many, hopefully, viewers online, because we are actually streaming this as an experiment, and seems to work fine. So thank you. We are using live peer if anyone want to try that. It's really fun. But that was not an advertisement. And thank you very much. And I'm really glad to see more and more people here, and hope to see you next time. So enjoy. Thank you.